In this video of StressOff, we are going to conduct finite element analysis of a 1 cubic meter steel cube using z88Aurora. Way to do it is, we'll create a new project, we'll create a new folder for that project, and then all of the files that are required, the input files and the output files, will be saved in this folder. Next, we need to copy or we need to import the step file. Now, we previously had created a step file of the cube when we were exporting it for PrepoMax. So what we'll do is we'll copy that and we'll add it to z88Aurora's folder. Next, let's just open the import dialog box, and we can go in and select the step file. Now the step file has been imported and it is a cubic meter block, as you can see here. So now let's go in and start all of the preprocessor. First thing is we need to mesh this block. Let's create a NetGen tetrahedron. We can just start with a linear mesh, and if required we can go for quadratic. For the value, let's just put in 101 millimeter. The reason we are using a value of 101 as the element edge is that last time we used 100, we got 11 edges on this one edge, or 11 elements on this one edge. I'm just trying to see if we just make 101 as the maximum value, do we get 10 edges on this or 10 elements on this edge or not. Let's just click on add and then create a mesh. Now, generating of that mesh was pretty quick, but we don't know what the mesh looks like. For that, we'll go up here and we'll click on visualization for a surface mesh. Let's quickly check if we did get 10 elements on one edge. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So by using 101 as the maximum element size, we did get 10 elements on the edge. So the meshing of this is done. After the meshing is done, let's go back to preprocessor, and then we'll need to first pick up all of the nodes for the boundary conditions, and for applying pressure we'll have to pick, or we'll have to select these surfaces. So we'll start with picking of the nodes. We'll show the bottom face, we'll click on one of the nodes, and then we'll say we would like to select the surface. As you can see, all of the nodes on the bottom face have been selected. So we will add this set and we'll call this set as DZ0. Next, we'll also first deselect all. Next, we are going to select all of the edges of this, or all of the nodes on this edge. So first let's pick on any one of the node on this edge, and then let's click on edge. So it selected all of these edges, and then we are going to say add set and call it DY0. Next, we'll click again deselect all, and then we are going to select all the edges or all the nodes on this edge. Click on edge and all of the nodes on that edge are selected. Click on add set and we'll just say this is DX0. After all of that is done, we'll need to go in and select the top surface. So we go in and say view select surfaces, and then we are going to pick any one of this node or any one of this surface element. We'll click on surface and it picks up all of the elements or the faces on that top face. We'll click on add set and we'll call this as press. Once when this is done, the nodal or in the pre-processing, we have meshed it and we have selected or we have renamed what nodes will be called what. The next thing we need to do is we need to add a material to this. If we go in and select engineering steel, details for the engineering steel, as we can see, Young's modulus is 2.1 e to the power 5, and that is the Young's modulus we want, and the Poisson's ratio is 0.3. We'll click on OK and we'll say define for all of the elements. Once when this is done, the material has been selected. Coming back to the constraints, let's go in and select dz0, give z direction displacement as 0. Then again, we'll have to give a name to this constraint, dz0, and we will add it. Now, I would like to first run a simulation where the bottom face, only the bottom face is constrained in z direction, and then we'll not constrain the x and y direction for this case. And then I would like to check if z88Aurora lets us run this simulation. Now after that, we'll go to press, and then we'll say it's a pressure load case, and then the value is 1 megapascal. We'll say that as, we can also say it's in z direction. We'll say PRE press, and then we'll add it. So the boundary conditions have been fixed here. So the only thing required to be done now is to go in and just run this simulation. So the failure theory we are going to use is 1 Mises, and if we want we can open the solver parameters, but because this is a simple, very simple analysis, we are not going to do that. I'll just say start calculation. We get the message solver ran successfully. We'll close it, and then we will start the post processing. What we want to see is deflected and undeflected both shapes. We would like to see mesh, and we'll also like to see the legend. Next, we are going to say I would like to see displacement in z direction. As you can see, displacements in z direction are visible, and the maximum displacement is on the top face, which can be seen by blue, and the maximum displacement is 4.76 micrometers. We can scale the deflection here. We can also have a look at the total displacement, and the total displacement is again on the top face, it is 4.43 micrometers. Let's have a look at the stresses at corner nodes. And what can be seen here is that stresses everywhere are shown as 1 megapascal. It is consistent except a few where it is 9.99 or 0.99 megapascal, except that everywhere is 1 megapascal. We can also check stresses per elements, and we can check stress as Gauss points. Now for the other software we have done stresses at corner node, so we'll stick to that one. So as you can see, just by having a boundary condition on the bottom face Z0, we could run this simulation. How about we go in and we add some more constraints. We add dy0 as 0 here. We'll again name it as dy0, and dx0 we'll give it a value of 0 and we'll name it as dx0. Now let's run this simulation. Again, solver said that the simulation was success. Let's go in and check all of the values. So the displacement is the maximum displacement in z direction is on the top face again, as we know, and let's show both the deflected and undeflected views. The maximum displacement on the top face is 4.76 micrometers. So the maximum displacement has not changed in Z direction. And the total displacement, again, it's in the top face and it is 4.7 micrometers. Now again, checking the stresses at corner nodes. And as we can see here, the stresses on corner nodes, even though it shows red and yellow, but there isn't much difference between the red and yellow, as it is all one till it starts going into the green zone. And again, that is well within the limits of the finite element analysis. Now we could have gone in and added a quadratic mesh, but we just stuck with linear mesh. So these results are within the boundaries of FEA, or finite element analysis. Now let's go in and quickly run the last simulation, which is, what if we delete all of this Y, X and Z, and then we say for dz0 we want all three X, Y and Z displacements to be 0, and we'll call it fixed. We'll add that, and then let's run this simulation. As you can see, this simulation ran successfully as well. So let's quickly go in and check the stresses. So the stresses at the corner nodes, as you can see, well, the stresses on four corners are more than 1.22 megapascals, but on the center of the block, the stresses are somewhere 0.55 to 0.6 megapascals. Now let's check the total displacement, and the total displacement, as we can see here, it is 4.32 to 4.75 micrometers. So that was the finite element analysis using Z88Aurora of a 1 cubic meter steel block. Thank you and see you next time.